Hi everybody. So in this video, we're going to look at the final conic section, which is a hyperbola. And this can be formed by the intersection of a cone with a plane that is steeper than the curved face of the cone. So you can see the hyperbola on this double cone here and here. And we can plot this on a Cartesian axis centered on the origin. And you can notice that the equation for the hyperbola is very similar to the equation of an ellipse, whereas this is a negative and for an ellipse this is a positive. So in example 1, given the general form of a hyperbola in Cartesian form, we're going to show that the intersections with the x-axis are at plus or minus a, and that it has asymptotes at y is approximately plus or minus bx over a. So to find where it crosses the x-axis, we need to say let y equal 0. And when y equals 0, the y squared over b squared will go. So we have x squared over a squared will equal 1. And then we can move the a squared to the right-hand side. So we get x squared is equal to a squared. And then we can square root both sides. So x will be equal to plus or minus a. And we can also prove why the hyperbola doesn't cross through the y-axis. If we now say, let x equal 0, then the x squared over a squared term will go. And we're left with negative y squared over b squared is 1. Or y squared over b squared is negative 1. And this can never be negative because y squared will always be positive and so will b squared. So because this can never be negative, it will never intersect the y-axis. And to find the equations of the asymptotes, well, we need to consider very large values of x and y. So if we say that x tends to infinity and y tends to infinity, then this 1 becomes negligible. So we've got x squared over a squared is approximately equal to y squared over b squared. And then we can move this b squared to the left-hand side. So we get y squared is approximately b squared x squared over a squared. We can take the square root. So y will be equal, or approximately equal, to plus or minus bx over a. And these will be the equations of the asymptotes here and here. Okay? In example 2, we're going to look at the equation of hyperbolas in parametric form. Okay, so for example 2, the first thing we've been asked to do is to sketch a hyperbola a squared over 9 minus y squared over 16 equals 1. So the first thing we need to do is we need to find where the curve crosses the x-axis. So we'll say let y equal 0, and then the y squared over 16 term will go. So we've got a squared will equal 9. So x will be equal to plus or minus 3. And now I can begin to sketch the hyperbola. So we'll have a root at positive 3 and a root at negative 3. And to find the equation of the asymptotes, we'll let x and y both tend to infinity. So now this 1 will become negligible, and we'll get x squared over 9 will be approximately equal to y squared over 16. Then we can move this 16 to the left-hand side and take the square root of both sides. So we'll have y is approximately equal to 4x over 3 plus or minus. So the equation of this asymptote will be y is approximately 4x over 3, and for this one, y will be approximately negative 4x over 3. So our hyperbola will be here for the negative values of x, and here for the positive values of x. Okay, so moving on to part B. Well, now we've been given a pair of parametric equations. We've been told that x is equal to 3 sec theta and y is equal to 4 tan theta. And we've been asked to show that these are parametric equations of this hyperbola. So what we'll do is we'll substitute x, 3 sec theta, into here, and this y, 4 tan theta, into here. So we get 3 sec theta all squared over 9 minus 4 tan theta all squared over 16. And we're told that this equals 1. When we square this x, 3 sec theta, we get 9 sec squared theta over 9. And when we square the 4 tan theta, we get 16 tan squared theta over 16. Again, equals 1. We can see that this 9 will cancel with this one, and the 16s will also cancel. And we should be familiar with the trigonometric identity, where 1 plus tan squared theta equals sec theta, or sec squared theta. Then we can use this identity by substituting 1 plus tan squared theta into here. So we get 1 plus tan squared theta minus the tan squared theta will equal 1. And we can see that this tan squared theta will cancel with this one. So the left-hand side will equal the right-hand side. So these are the parametric equations that will give us this hyperbolic Cartesian equation. But we can form this Cartesian equation with a different pair of parametric equations. We can use x equals 3 cos theta and y equals 4 sine theta. I can show you why this works. We'll substitute the 3 cos theta into here, and we get 3 cos theta all squared over 9 minus 4 sine theta all squared over 16 equals 1. When we square the numerators, we get 9 cos squared theta over 9 minus 16 sine squared theta over 16 equals 1. Again, these 9s and 16s will cancel, and this hyperbolic Pythagorean identity, cos squared minus sine squared, does indeed equal 1. Okay, so I hope that's giving you an idea that we can represent a hyperbola conic section as a Cartesian equation, parametric using sec and tan, and parametric using cos and sine. In example 3, we're going to look at how to find a tangent to a hyperbolic curve. Okay, so finally, in example 3, we've been told that a hyperbola has parametric equations x equals 2 sec theta and y equals root 3 tan theta. And we've been asked to find the equation of a tangent to the hyperbola at the point where theta equals pi over 6. So the first thing we're going to do is we need to consider the equation of a tangent to a curve. And we should be familiar with this equation. So we need to work out the m, which is our gradient, our x1 value, and our y1 value. Well, we can work out the x1 and y1 values by substituting this theta equals pi over 6 into here and here. So x1 will equal 2 sec theta, or pi over 6, and this is 4 over root 3. And y1 will be root 3 tan of pi over 6, and this is 1. So all we need to do now is to work out our gradient, which is dy by dx. And to work out dy by dx, I'm going to differentiate each of these parametric equations and then use the chain rule. So dy by dx will be dy by d theta multiplied by d theta by dx, or dy by d theta divided by dx over d theta. Okay? So dx by d theta will be the derivative of 2 sec theta, which is 2 sec theta tan theta. And dy by d theta will be the derivative of root 3 tan theta, which is root 3 sec squared theta. And these derivatives are standard derivatives given in the formula booklet. So now, dy by dx will be dy by d theta, so root 3 sec squared theta, over 2 sec theta tan theta. And we can see this squared will cancel with this one. So we have root 3 sec theta over 2 tan theta. And then we can express sec theta as 1 over cos and tan theta as sine over cos. So dy by dx becomes root 3 over cos theta multiplied by cos theta over sine theta. And then these cos thetas will cancel. So we're left with the gradient dy by dx will be root 3 over sine, this should be 2 sine theta. And we've been told that this theta is pi over 6. So at theta equals pi over 6, dy by dx, or our m value, will be root 3 over 2 sine of pi over 6, which is root 3. So now we have our gradient, our x1 and y1. We can substitute them into this formula. So we get root 3 lots of x minus 4 over root 3 will equal y minus 1. We'll multiply out by this root 3. So we get root 3x minus with 4 will equal y minus 1. And then we'll move the negative 1 to the left-hand side. So y will equal root 3x minus 3. Okay? Well, I hope you found that useful, and that's given you a clearer idea on how to work with the Hyperbola Conic section. If you did find that useful, please like and subscribe, and you can download the full lesson and worksheet from my website, mrmathematics.com. There's a link in the description below. Thanks again, and take care.